Hello students, and welcome to part 2 of section 3.1 on the basics of probability. So in the previous video we did a brief introduction to the idea of random phenomena and probability, and we did a few examples from the homework. So the last example we did was question 4 from the homework. Just to quickly recap, what we did was we took the number of people in the table that were very prepared for a power outage, natural disaster, or terrorist attack, and then we divided that by the total. Okay, the total of these numbers here ended up being 2195, and when you do 241 divided by 2195 and round it to 3 decimal places, the answer ended up being 0.110. So the 9 here gets rounded up to a 10, so you replace the 9 with a 0, and then you carry the 1 over to the 0, so that's how we got the answer of 0.110. Let's go to the next question. And it says, to use the frequency distribution, which shows the number of American voters in millions according to age, to find the probability that a voter chosen at random is in the 18 to 20-year-old age range. So according to the table, there were 4.9 million voters in that age group, 18 to 20. So remember, the basic idea is that if we want to find the probability of an event, right, we find the number of ways that that event can occur, and then we divide it by the total number of possibilities. Okay, so we know the number of voters in the 18 to 20 age group, so it's 4.9 million. Okay, but the question is, do we know the total number of voters according to the table? Okay, that's the next thing we need to figure out. So to get the total, we have to add up all the numbers in the frequency column. So 4.9 plus 8.5 plus 23.7 plus 22.6 plus 52.3 plus 28.2. Okay, so there's 140.2 million voters altogether. So 4.9 divided by 140.2. Okay, and according to the directions in blue, it says we're going to round to 3 decimal places as needed. Okay, so our probability is represented by this decimal here. So 0.03495. So to 3 decimal places, so 1, 2, 3 digits to the right of the decimal point is what we're rounding to. So the 4 here is in the rounding position. So we look over to the next number to the right. So if the next number to the right of the rounding position is 4 or less, let it rest. And if it's 5 or more, let it soar. So if we let it rest, that digit in the rounding position stays the same. If it's 5 or more, if the number to the right of the rounding position is 5 or more, let it soar. So then we increase that by 1. So we can see that the number to the right of the rounding position is 9, okay, which is 5 or more. So that 4 in the rounding position is going to go up to a 5. The answer is 0.035. Okay, so same type of question. It says use the frequency distribution, which shows the number of voters in millions according to age, and we want to find the probability that a voter chosen at random is in the given age range, so that they're not 65 years old or older. So first of all, how many are 65 years or older according to the table? So according to the table, there are 27.9 million voters who are 65 or over. So let's keep that in mind. The total number of voters according to the table, so if you add up all the numbers in the frequency column, we're going to get 149.2, so 149.2 million voters. Now you may have noticed that the numbers in the table changed from the previous question. So in other words, we can't use the total that we got in question 5 to answer question 6, unfortunately. So off camera, what I did was I added up all the numbers in the frequency column, and I got 149.2. And we want to know the probability of picking a voter who is not 65 years or older. So one way to approach this is to add up all the frequencies that correspond to the age groups that are not 65 and over, okay, and add those numbers up, and then divide that by the total of 149.2. Another approach, which might be a little easier, is if you take the total, which is 149.2, and then subtract from it the total number of voters that are in that age group, 65 and over. So 149.2 minus 27.9. Okay, so we're taking the total number of voters and subtracting from that the number of voters in that age group. Then we get the remaining voters that are not 65 and over. So which according to the calculation here is 121.3 million. So we're going to take 121.3 and then divide that by the total of 149.2. So the number of voters not in the 65 and over age group divided by the total number of voters, and then rounded to 3 decimal places to 0.813 will be the answer. Okay, and again, if you're not comfortable doing that way, go ahead and add up the numbers in the other age groups and see that it's equal to 121.3, and then divide that by the total of 149.2, and you'll still get the same answer. Okay, let's go ahead and go to the next question. Okay, question 7 says the access code for a garage door consists of 3 digits. Each digit can be any number 1 through 9, and each digit can be repeated. And we're going to answer parts A through C. So the first part asks, find the number of possible access codes. Okay, so try to imagine the example in the previous video, right, where we were picking the numbers for a combination to a lockbox. Okay, but this time we're picking 3 numbers to get an access code. All right, and we're still using the digits 0 through 9, or rather 1 through 9. Okay, so the problem says 1 through 9, okay, rather than 0 through 9. Okay, and there doesn't seem to be any restrictions on the digits that we can use for this access code. So I'm going to go ahead and put 2 back in here. As one of the possible digits. Okay, so once again, each digit can be any number 1 through 9, and each digit can be repeated. Okay, so this is an application of the fundamental counting rule that we learned about earlier. Okay, so there are 9 digits 1 through 9, and because we can repeat them in our access code, okay, each number in our access code has 9 possibilities. Okay, and according to the fundamental counting principle, okay, we multiply the number of possibilities for each number in the access code to get the total number of access codes. So that's 9 times 9 times 9. Right, or you can do 9 to the 3rd power. Right, so find the exponent button on your calculator. Right, and we're going to get 729 access codes that are possible. Okay, part B says, what is the probability of randomly selecting the correct access code on the first try? Okay, so if you're just randomly picking digits to try to break the code, right? So you have one possibility, right? So one chance of breaking the code. Okay, out of the 729 codes that are possible. Okay, so we have 1 try. So in the numerator we have 1. And then in the denominator, we have the total number of codes that are possible, which is 729. So we're literally going to do 1 divided by 729. Okay, and as you answer the questions, pay attention to how many digits it asks you to round the answer to. Okay, so our answer is 0.0013, so to 3 decimal places, so 3 digits to the right of the decimal point would be 0.001. Yeah, so not a very good chance, very small chance that you would actually guess it on the first try. Okay, and then the part C says, what is the probability of not selecting the correct access code on the first try? So if you don't get it, if you pick one of the other codes, remember there's only one code that will break it, right? So if you don't get it on the first try, right, it's the total number of codes, which is 729, right, minus the one correct code that it is, okay, which is 728. So that leaves 728 other codes that are not the actual access code. So then we need to divide that by 729. You get the number 0.9986. Okay, and we're going to round that to 3 decimal places, so that 8 there, which is in the rounding position, so it's 3 digits to the right of the decimal point. Right, in order to round it properly, we look at the next digit to the right. Okay, since that next digit to the right is 5 or more, we're going to let it soar, so that 8's going to get rounded up to a 9. And then all other digits remain the same, so only that 8's being changed to a 9, so the answer is 0.999. So there's a very high probability that you will not select the correct code on the first try if you are randomly guessing the access code. So another way to get the answer to part C is to take 1 and then subtract from it the probability that you got on part B. So 1 minus 0.001. Okay, and that's based on the fact that if you do guess the correct access code on the first try, right, that's the opposite of not getting the access code on the first try. So the event of correctly guessing the code on the first try, and then the other event of not correctly guessing it on the first try, those are called complements. So whenever you're asked to find the probability of a complement, and you know the probability of the original event, right, then the probability of the complement is equal to 1 minus the probability of the original event. Okay, you can verify that in the book, what I just mentioned. So I encourage you to look at the examples in the book, so they're much like the ones in the homework, if you need extra practice. Okay, and then talk about the different types of probability, which we won't go through. All right, and it's important to know that the probability of any event will always be a number between 0 and 1, and that's what this is saying. So in other words, you can't have probabilities that are less than 0. So there are no negative probabilities. And likewise, you can't have probabilities that are greater than 1. Right, and on page 138, it talks about the definition of the complement of an event. So, and that's what we did in the previous example. So to find the probability of the complement, so the complement of an event is notated with an apostrophe. So this means probability of E complement is equal to 1 minus the probability of E, and that's the principle we were using to answer part C of this question. Okay, so let's go to question 8. And I'll skip over that because it's longer than I have time for. So question 9 says the probability of an event is 0.36. So find the probability that the event will not happen. Okay, so this problem is an application of the complement rule that I just mentioned. So it's 1 minus 0.36. which is equal to 0.64.